My dear participants, very good morning to all. The resource person by Pradeep Kumar from IIT Hyderabad is joining the session within 2 minutes. Please log on and stay with us. He is dealing with wind power and related topics. He is a very senior person. Please stay with us. Thank you.
Good morning, sir. This is Pradeep from IIT Hyderabad.
Yes, sir. Good morning, sir.
Good morning, sir.
Good morning. Yes.
Yes. Good morning, sir. Very good morning.
Yes, very good morning.
Today's session, our presenter is Dr. Pradeep Kumar A. Is Associate Professor in IIT Hyderabad. He completed his Masters from IIT Mumbai in 2006. He also completed his PhD same from IIT Mumbai in 2012. Presently, he is working as Associate Professor in IIT Hyderabad. Prior to joining in IIT Hyderabad, he worked as Assistant Research Professor at the School of Electrical and Electronics Engineering at Washington University in Washington. He also worked as a Research Officer of India's Smart Grid Forum. His areas of research interest are smart grids, power system control centers, information technology architectures, ontologies for power system events, common information model, interpretability and standards. Apart from these activities, he is passionate about teaching and enjoyed delivering lectures to young engineers on core power system concepts, advanced smart concepts. He guided many research scholars in his career. So we need his sir's opportunity with these presentations. Thank you, sir. Thank you very much. Please continue. Sir, continue.
Sir, please unmute yourself, sir.
Sir, unmute. Sir, please unmute, sir.
Yeah. So, yes, I have unmuted. You are able to hear me now?
Yes, sir. Thank you, sir. Yes, sir.
Okay, so good morning, everyone, and thank you for the kind introduction that you have given me. So, I would like to begin the session on wind energy. So, let me show my screen. So, now can you see my screen? So I just want to confirm you are able to see my screen, right?
Yes, sir.
Yeah. So this is an overview of wind energy systems. I would like to present that. And in this, one of my student, Miss Divyanshi, has helped me in compiling the materials. So actually, I have not made it like a full presentation because I want to cover some kind of hand written things also. Because it will be, rather than slides, it will be more interesting if you see the handwritten derivation, some interesting findings. So, but before I jump into that, so I have a YouTube channel, as it was just mentioned. So, in which there is one of the playlist about renewable energy. And if you look at the right side part in this, that is introduction to wind energy system and then wind energy economic considerations, then mathematics of wind power generation and wind power scenario in India. So already I have created some of these videos which are available online. So in addition to what today's session, you can also refer to these sessions. And apart from these videos, I also make a lot of other subjects like, the basics like DC machines and transformers and electric circuits, magnetic circuits. So all these courses which I teach, I have also made videos on YouTube. So my YouTube video name is Pradeep, my own name. So you search on YouTube, and you can, while you are there, you can subscribe, and you can look at the playlist. Different playlists are there, and you can follow that. So with that, I'd like to come to the session. It is not some of the concepts. So first is, the brief introduction, and then mathematics of wind energy, global scenario, Indian scenario, and some concluding remarks. Okay, so with this, I think I'll shift to another thing. So instead of directly jumping into mathematics of wind energy, I would like to talk about the scenarios. So and then maybe next we will go into that. So again, I hope you are able to see my screen. So
Yes,
I have listed some of the bullet points here, and one by one we'll try to go. And these are some of the general things that you should be aware of while working with wind power. So wind power scenario in India. So wind power generation capacity in India significantly increased in recent years. Now, in fact, not only wind, even solar and all also picking up very fast. So as of 31st August 2020, so this is slightly 2-3 months old data. So right now we are in November 2020. Okay, so as of 31st August 2020, the total installed wind power capacity is 38 gigawatt, the fourth largest installed wind power capacity in the world, and the total renewable. So India. So still we have to cross 100, and we have to go to 175 in next 2 years, which means almost we're going to double our capacity in next 2 years. So it is a huge increase that is there in the entire renewable energy, out of which about 40% is about our wind power itself, 38 gigawatt. Now this data is as of 31st August 2020, and for the information of everyone, if you want to find out the latest installed capacity, so the website is CEA. So you go to Google and type cea.co.in. No, I think not this one. Simply just type CEA. Central Electricity Authority, CEA. So you can find that link, and then once you open, so you will have a lot of reports. On the left side, you can see daily report, executive summary, installed capacity, and all these things. So for example, if I again at the top, if I go to this one, reports, so I can get a monthly report here. So you can go to monthly report tab. So before that, if I again go back, there is a slideshow on the home screen itself. So this is the official government website of Central. So transformation capacity, some data and all it is given. So you can also refer to that. So now coming to these reports. So far now October report is not yet out, but September report is available. So if I click that, and if I go down and then search for wind, so this is generation. So now if I go to capacity, so here again you can confirm. So 38.124 is the wind power capacity. So what you can see right now on your screen is the breakup of the renewable energy in India. So this is in megawatts. So small hydro is 4,739 or about 4,734. Sorry, 740, and wind power is 38.12 gigawatt or 38,124 gigawatt. So earlier it was just 38 I mentioned. So meanwhile 124 megawatts have been added in this just 1 month. So probably the last month. Okay, let me also open that. If I open the August 1. And search for wind. So here you can see in the month of, as of 31st August, wind power was only 37,999 or 37 gigawatt, you can round off. Now that figure now coming in just 1 month, it has become 38,124. So you can see constant growth. So in 1 month itself, 124 megawatts of wind power has been added across the country. So like this, you can track all the, not only this, all the other things. So while we are at it, let's have a look at the solar power also. So in the month of 30 September 2020, of solar is now if is 0.73. Okay, so 35,739 gigawatt was there. Now it is 36,000. So almost how much? Almost 300 megawatts of solar power has been added in last 30 days in the month of September. So these numbers are constantly increasing, and the resource that I just showed you is the CEA website, Central Electricity Authority. So if you want to get the latest information about not only that, there are different reports, regulations. In fact, there are daily reports, executive summary, power maps, different tenders, circulars. So much information is available on this particular website. So you can refer to that. Okay. So let me come back to our document. So here, maybe I can just add a point here. Okay, I'll just leave it for now. So according to the statistics presented in the World Wind Energy Association, so there is another resource, World Wind Energy Association. The overall capacity of all wind turbines installed worldwide as of 2019 reached 650.8 gigawatt. Okay, so worldwide is 650, whereas we are already at 38. Okay, so it's a good respectable number. So if I take a percentage, so as of 31st August, the national electric grid in India has installed capacity of, okay, so this 372 gigawatt is the overall Indian grid capacity, out of which wind power capacity is about 10% of total installed capacity. Next, total renewable energy installed capacity in India is 88. So again, I mentioned 89, and 23.8% of the total installed capacity. Wind power installed capacity is about 42% of the total renewable capacity. So India has the high wind energy potential. Okay. So what is the potential? So 302 gigawatt at 100 meters and 695 gigawatt at 120. That is our entire potential. How much of the potential is realized? So 302, and we just saw here 38. So almost just about 10% of the potential only we have realized. So therefore, we can even we can step up our wind power. Even 10 times we can increase, still we will have a potential available in our country. So there is a huge scope of growth of wind power. So next point, the Ministry of New and Renewable Energy, MNRE, has set a target of installing 175 gigawatt of renewable energy capacity by 2022, which includes 100 gigawatt from solar, 60 gigawatt from wind, 10 gigawatt from biopower, and 5 from small hydropower. So if you look at this breakup, see, by 2022, right now we are at 38 gigawatt, so it should become 60 gigawatt. Okay. So whether we'll be able to get 60 gigawatt or not. Okay. So, but going by the trend, it is definitely achievable. Next is we talked about solar, right? So solar, we want to touch 100 gigawatt solar by 2022. What is the solar? We were just 100 is achievable. So this 100 gigawatt also has a further split actually, 60 plus 40, where 60 should come from rooftop and 40 should come from large projects, funded by private and government and like that. So, or it might be the other way around, but to be safe, you can assume 50-50. So even common people like you and me, the regular consumers, can also contribute to the India's target of 100 gigawatt solar by installing rooftop solar on our houses. Even if we do in kilowatts, across millions of people, it will add up and become gigawatts. So that is about that. And then let's continue. It is likely to fall short of its ambitious wind energy target by up to 10 gigawatts. So this is like again a little bit of prediction, but then let's see how it goes. The country's total wind energy capacity would only reach 50 by 2022 as existing pipelines and new auctions face multiple challenges. So, but then if still there is time, so if things get resolved, it is also possible to cross that. Now coming to wind energy generated. Okay, so as per CEA report of July 2020, total wind energy generated in India for the month is 6966 million unit, like this. So this is about July 2020, right? So let's see if we can find the latest information. So I'll again go to the same executive summary, and then I'll just search for wind. So here, if you again so on your screen again, we can find out what is the all India generation from renewables. So this is as of August 2020. For the month of August 2020, from wind we were able to generate 9,645 million units. So these are in figures are in million units. Okay. So 9,645 million units, and compared to last year, it is slightly reduced. So due to some reason, so the wind again depends on the weather. So this is one of the issue. Whereas solar, you can see significant increase from the last year for the month of August 2020, and all other sources are also mentioned here. Okay. So if I go back to the executives, whatever I was preparing here. So here I will say August. So now I have the data of August also. Total wind energy generated. So instead of 6966, right now what we have 9645. Okay, so it's a good increase. 9645 million units. So which is also 9.645 terawatt hours. So now we also know the installed capacity. So again, going back for the July data, so here it is August data, whereas this is July data. So going back to August data, so what I get is 6.966 terawatt hours divided by 32 point. So this is the capacity multiplied by 24 hours multiplied by 30 days per month. And this is for connection of units and conversion to percentage. So finally, what we get is capacity factor of wind energy is only 25%. So which means because the wind output is not constant throughout the period, so sometimes it may be more, sometimes it may be less. So therefore, the capacity factor is only 25%. Okay. So which is also like in some places depends on your location. So if you locate it by studying the weather patterns and where constant wind velocity is there across the year, so then become more. Capacity factor is less. The variations also intermittent, wind variations are there, which are all technical challenges. But then, since it is clean energy, since it is renewable energy, definitely we should go with the wind power. And of course, there is no fuel cost, no running cost, so it is also very advantageous in that sense. Now, just one more point there, that is the calculation. So I'll just match this point into the next page. So in the month of July, the total electrical energy demand met by India is 121.71 billion units. So total electrical energy demand met. from which 13.242 billion unit is from renewable energy sources, out of which 6.966, that is just now what we mentioned, is through wind energy. So although wind installed capacity is 23%, 23.8%, the wind energy consumption is only 5.723%. So the capacity may be, capacity wise it is 23.8, but that is the power wise, whereas energy wise it is only 5.723%. That is for the month of July, but of course we can also now calculate month of August and all, so we can do that. Now coming to this, largest wind farm in India. So Muppandal wind farm of capacity 1500 megawatt. So you can, I think there will be a lot of information available on this. So you can just simply search for the title and you'll get the information of this particular Muppandal wind farm. So the location is somewhere near to the southern tip of India, the Muppandal wind power, and capacity 15. We can see Kanyakumari again. It's a very historic and beautiful place, the southern tip of India. So you can see. And while we are here, there is also detailed information that is wind power in India, and so there is another page about wind power in India. So anyway, let's come back to this. Now, second largest wind farm in India is Jaisalmer Wind Park of capacity 1.64 megawatt. See, again, all these statistics are as of July or August, the second half of the 2020. So probably in the future years, these may become, the largest may become the second largest if something else comes up. The Ministry of New and Renewable Energy set a target of 5 gigawatt of offshore wind power by 2022 and 30 gigawatt by 2030. Now, this is something new. So offshore. So offshore means it's not on the land, it will be on the ocean. There will be a wind power. So the target is 5 gigawatt for that. And that is by 2022 and 30 gigawatt by 2030. So again, you can see almost target of 2022 to target of 2030, it's increased by 6 times. So again, if you are working in the area of offshore wind power, there's so many opportunities again might be there in India. Now, offshore wind power plant in India, there's only 100 megawatt demonstration project planned off the coast of Gujarat. So still it's just in the very initial stages. Now coming to Tamil Nadu, Tamil Nadu has nearly 9.3 gigawatt of cumulative wind installations. So Tamil Nadu is actually the leader within the India out of all the states, representing a 24.77% share of total installed capacity in India as of 2020. So the reference for this is again here, the CEA website I have given. So now this is one more interesting figure which I got from again online source. This is actually to the scale, and this shows the evolution of the size of the wind turbine. Single wind turbine, how much it can generate. So here, so for example, as you increase the height, the more energy can be extracted from the wind. So therefore, we have to go for larger height. And at the same time, if you increase the length of your wind blade, the overall cross-section area of the wind turbine will be more, and you can generate more. So back in 1980, the tallest wind turbine was about only 15 meters, and it could only generate about 10 kilowatt. I think 0.01 megawatt is like 10 kilowatt. Then 10 kilowatt became 100 kilowatt, then became 500 kilowatt, 600 kilowatt, and slowly we entered into the megawatt range. And then by the time 2010, a single turbine can generate 7.5 megawatt, which is a huge power already. And now, as of 2020, turbines are available, which can generate turbine can generate 20 megawatts of wind power. So these are some of the interesting scales that you should know about the wind turbine. So of course, some interesting mathematics also is there in it, which we are going to see in the next section. But then I thought I will show this. And let us complete this part, that is wind power scenario in the world. So according to the statistics presented by the World Wind Energy Association, the overall capacity of all wind turbine installed worldwide as of 2019 reached 650.8 gigawatt. Okay. So again, if you go to this WWEA, so you will find some more information on that. So this is the website of WWEA, and so there is a home, and then mission, all these things, working groups are there, and then webinars are available on this. So let's look at what kind of webinars are available. So there are some register here for free. Okay. So there are some free webinars are available, previous webinars. So recordings are also available. So by the way, I could not see this. I would have covered some points from all of this if I had seen this earlier. But let's see, wind power markets around the world. There is a webinar. Okay. And wind community power matters in times of crisis. So community power industrialized, sorry, this is not wind, this is Y. So this is talking about community power. So I think wind power and renewable energy policies, what is best to reach 100% renewable. So this is a presentation about policies and achieving energy self-sufficiency with small wind turbine. Okay, so that is also there. Community power partnership for developing countries. So there are a lot of resources. Education and training for wind power and renewable energy. So wind power markets around the world, half yearly review. So the Asia and Australia. So all over the world, all these things are available. So let's just for sample, let's open one. So wind power markets around the world. So this is the previous webinar I'm just trying to open. So this was delivered in April of 2020. And yes, it is available here. They have kept it nicely. They have kept it in YouTube itself. So good. So again, people, you can refer to this welcome and global market overview. Okay. So I'll just, for the sake of, I'll add it as one of the resource here. I'll go to the end and add. So webinars on wind. Okay, so let's finish this 2-3 points which we have. As of 2019, China tops the chart with 236 gigawatt of installed capacity, followed by United States 105 gigawatt capacity, and Germany 61. So actually India is number 4. So first is China, then US.
Sir, please unmute, sir. Sir. Hello, sir. Sir, please unmute your system, sir. Hello, sir. Hello. Hello, sir. Please unmute, sir. Sir, hello, sir. Hello.
Yes, sir.
Okay, sir.
I'm sorry, there was some interruption. I think.
Okay, sir.
Okay. So, shall I continue from where I left off?
Okay, sir.
Okay. Yeah. So I was talking about this top 10 countries. So this is, I think this is a cumulative number, and this is the added in that particular year. So that's why the numbers are like this. So you can notice that, as I already mentioned, 230 is China, 105, 61, and 37. Okay. So let's. I think this part I have completed. So let me now pause for a minute, and then I would like to get some questions from the audience on this thing. So yeah. So any questions you have so far? So I'd just like to pause for 1 or 2 minutes to get some questions. I noticed Dr. K. Srilata has raised her hand. So do you have a question? Dr. K. Srilata.
You communicate that all are being auto-muted and your question cannot be raised. The question chance will be given at the end.
Yes, ma'am.
I am giving time for question and auto-mute చేసినాం. ఎవరైనా question ఎక్కడ అందరూ unmute చేస్తున్నారు. I think around 20 participants who wants to ask any question can ask it. Otherwise, shall I continue and ask you to continue? Technical issues కూర్చున్నప్పుడు చూడాలమ్మా.
Yes, participants.
Sorry, again there was an interruption.
Okay, sir. Thank you.
So was the problem from my end or your end?
A problem may be your end, I think, sir.
Okay.
It is okay, sir. Participants, anybody, please, if want to ask doubts, please raise doubts.
I'm just waiting for 2-3 minutes for taking some questions, and then I'll continue with the mathematical modeling.
Okay. Okay, sir. Now, okay, sir.
Yeah. Okay.
Okay, sir. Thank you.
So I just shifted to pen and paper mode. So I think you are able to see my screen, right? Full screen.
Yes, sir.
Okay. So at my end, I'm not able to get the full screen. So just a minute. Okay, so now what I want to cover is some interesting finding regarding the mathematics of wind power. So let me begin by writing it here. So usually this thing is not covered in many of the wind power related courses or so. So it is a little bit interesting. So I thought I will show that, and it's also an application of where you can use this differential equations, minimizing, maximizing. So it's one of the applications. Okay. So to better understand this, let me draw a diagram. So let's take this as a wind turbine. So you can see this is the ground and this is the wind, and then there is a all these wind blades are there. Now what is the way it works? So if I mark the circle that is formed by the turbine blades, so there will be kinetic energy. So I call it K1, kinetic energy. The Because the wind will not stop, it will continue to flow. Kinetic energy 1 and kinetic energy 2. So compared to these two, so obviously the here whatever is the difference, that will be the mechanical energy converted into electrical energy. So let's right now I will call it mechanical energy itself. Not worried about the electrical losses and things like that. So from this I can clearly make an equation. So the mechanical energy generated is kinetic energy 1 minus kinetic energy 2. So please feel free to ask doubts if you have anything in between. So like this. Now so obviously I want to maximize the mechanical energy. Okay? So in order to maximize the mechanical energy, how you can do that? So there is a control variable here. So the control variable is pitch control. So what is a pitch control? So you can that blade which is there, the angle of the blade, So if you make the angle parallel to the wind, that means most of the wind will simply go flow through the blade and it will not impact the blade. But then if the blade is turned such that it is blocking the wind, then more energy can be extracted. So by controlling a proper angle, we can control how much force the wind is exerting on the blades and like that. So so now for the next 10-15 minutes, we would like to see how to get that maximum MPPT. It is called, in solar it is called MPPT. Same thing you can apply in wind also. Maximum power, how to track it. Okay. So for this you also need to know about one parameter called rho. Okay. So rho is density of air. So and the unit of rho is kg per meter cube. So kg per meter cube. So in other and its value is 1.225. It's the symbol is rho. Okay. So what is the meaning? So if you take a glass box of 1 meter cube glass box, okay, 111. So this 1 meter cube glass box with the air, if you take the weight, measure the weight, let's say it is coming 3.225, then you remove all the air from it and then again take then the difference is the weight of the air. So it will come something like this. Okay, so this is about the density of air. Okay, anyway, so now coming to this kinetic energy. So what is Ke? Kinetic energy is nothing but half into m into v1 square. Okay, so what is this mass of the air? Because the air itself or wind itself is coming. So what is the mass of the air? And multiplied by v1 square will be the velocity. Assume that v1 is a velocity in meters per second. Similarly, here it will be half into m into v2 square. So the mass of the air remains same because we are not sucking any air into the wind turbine. Whatever air comes, it just flows. So half m square is the here. So therefore, what is our mechanical energy? So mechanical energy is nothing but Ke1 minus Ke2, that is half m v1 square minus half m v2 square. So which is nothing but half m you can take common, v1 square minus v2 square. So here we get mechanical energy. Now how to convert energy into power? Okay. Energy into power, rate of change of energy is nothing but power. Okay. So you divide both sides with respect to time. Okay. So delta t I keep here and here I will keep delta t. Okay. So both sides you divide by delta t, then we get the power. Okay. So now I will rephrase the symbols now. Pm, mechanical power, is half this quantity m by delta t and multiplied by v1 square minus v2 square. Okay. So I'm getting like this. So what is this quantity m by delta t? So what is the unit of this? So the m by delta t. So if this is the first page. Now if I go to the next page. So by the way, you are able to see my handwriting properly, right, on your screen? Just want to confirm. Yeah. So what is this m by delta t? So m by delta t is look at its units. It is kgs divided by seconds. So kgs per second is nothing but flow rate, and flow rate can be denoted by q. Okay. Now I want to know what is this q. Okay. Now we have to introduce one more term here. I go back to the drawing. Here the velocity is v1, wind velocity is v1. Here the wind velocity is v2. In between, let's call it wind velocity as vt. Vt is the wind velocity at the turbine. Okay. So if I take the quantity rho a vt. So what is the unit of this? Rho into a into vt. Rho is density, that is kg per meter cube. And A is area. Area is meter square. The area means the circular area, whatever the length of the blade it will become the radius, and that circle will be the area. And velocity. Velocity is again meters per second. Okay, so like this. Now, if I cancel out the meter cube with meter square and another meter, then I get the unit kg per second. So basically, this is nothing but the flow rate. So the quantity Q can be represented as this. So therefore, from this I can say m by delta t is nothing but rho a into vt for this particular example. Okay. So this one, let's say this one is equation 2 and this one is equation 1. So in one I can substitute 2, then I'll get Pm, mechanical power, is half rho a vt multiplied by v1 square minus v2 square. Okay. So I am getting an equation like this. Let's call this equation 3. Okay. So I hope so far you are able to follow. Okay. So before I go further, one point I can just comment about what is this v1 and v2 once again. So let me once again take a fresh page. So here there is a wind turbine. Now V1, V2. So obviously, in order to maximize the kinetic energy, why not make V2 equal to 0? If I make V2 equal to 0, that's a good idea, isn't it? So, but actually it is not, because if V2 equal to 0, that means on the backside of this, all the wind is stationary. So if the wind is stationary here, it's like a traffic jam. No further wind can flow. So from this side, the wind is anyway continuously coming, but where it will go? It cannot completely vanish. So therefore, some velocity should be there so that wind will be able to pass on. So it cannot have, so V2 is equal to 0 is not possible. Okay. So because the wind will not be able to go. Now we can make another condition. You can check V1 equal to V2. So V1 equal to V2 is again obvious. If both the values are equal, that means you are not extracting any energy. So this is also not possible. So there will be some value of V2 in between. So if I take a graph like this, 0 and to V, for a particular value of V2, I can get the maximum power PM. Okay, so that is what we want to find out. For what value of V2 are we getting the maximum power? So yeah. So let me go back to again this drawing. So I was here. Now in the next step, what I would like to do is eliminate this T. Okay, so how to eliminate T? So again, referring to this turbine. So at this point, you can apply F equal to ma. Okay, so if I write force is mass into acceleration. Okay. So, but what is acceleration? Acceleration is change of velocity, right? So force again equal to mass into acceleration is what? Rate of change of velocity. Okay, so Vt divided by delta t. So again, our friend is there, m by delta t. So what is m by delta t? Already it is there in equation 2, which is nothing but force is nothing but rho a Vt again multiplied by Vt. So I'm just substituting m by delta t from 2 to here. Now again, what is this? Force is rho a Vt square. Okay. So let's call this as one more equation 4. But what is the force into velocity? So this is nothing but power input to the turbine, right? So force into velocity will be the power input to the turbine. Oh, I'm sorry. I just made a mistake here. So let me just remove this. See, force is m by delta t into Vt. So this is what we got here. So from here, what I want to do is force into distance is work done, right? Force into distance by time is nothing but so again I will take one more Vt. In other words, I will multiply Vt on both sides. So this distance by time is again Vt. So if I do that, so then I will get F into Vt is nothing but rho a Vt square V1 minus V2. I'm sorry, I have to. So this is not correct. See, force into distance is nothing but work done. Work done by time is nothing but PM. So that is why I was getting confused. So this will become PM, and then now I can substitute the PM which I got earlier from 3 to here. So ultimately, half T value V1 into V1 plus V2. So whole of that will be equal to rho A Vt square into V1 minus V2. So like this, I'll get from both of this. So from this, I can eliminate Vt. So how I can eliminate is rho will get cancelled, A will get cancelled, V1 minus V2 will get cancelled, and finally Vt square will get cancelled. So Vt will be equal to V1 plus V2 by 2. So I'm sorry if I confuse you a little bit in between, but if you separately do it on your own, definitely you will come for this particular conclusion that Vt is nothing but the average of V1 minus V1 and V2. So this is one finding we got here. So let's call this equation 5. So from this now I can now go back to equation 3 and substitute this Vt value and express only in terms of V1 and V2. So I'll get Pm equal to half rho A. So in the place of Vt, I put V1 plus V2 by 2 and then V1 square minus V2 square. So this I can expand. So 1 by 4 rho A. So here it will be, if I open this bracket, so V1 cube minus V1 V2 square plus V2 V1 square minus V2 square. So again, bear with me because it is a little bit mathematics, but it is very worth it. As I mentioned already, not all places you find this information. So that's why. Now from this, what I want to do is I'll take Pm equal to 1 by 4 rho A. I'll take V1 cube common. So then it will be 1 minus V2 by V1 square plus V2 by V1 minus V2 by V1 whole cube. So like this I'll get if I take this common. So now if I substitute V2 by V1 fraction as A, then I'll get Pm equal to 1/4 rho A, some kind of constant minus term. So some constant multiplied by that. Now I want to maximize the mechanical power. Okay. So I hope I'm on screen. Okay. So now I want to maximize the mechanical power. So simply differentiate and equate to 0. So these all are constants. The area of cross section is constant, rho is constant, and V1 is not our control variable, so it is assumed to be constant. So now I can do this. So now if I differentiate with respect to A, so I get this constant. So right now I'll not worry about it. So the differentiation of 1 is 0 and 2A and here 1 and then minus 3A square. So this differentiation, if I make it equal to 0, I'll get a maxima. Okay. For maxima or minima, but anyway, here it will, in this case, it will be maxima. So now I want to solve for A. So I get 3A square. I'll just cancel the minus, plus 2A minus 1 equal to 0. Okay. So from this, I'll get this one. So it's a quadratic equation. So A is minus 2 plus or minus square root of 2 square minus 4 into 3 into minus 1. Okay, so by 2A. So that is by 2 into 3. So this is nothing but so this will become plus, so 12. So this is 16 by 6. So this I'll get minus 2 plus or minus 4 by 6. So either I'll get 6 by 6 or minus 1 by 3. Oh, I'm sorry, minus 6 by 6 or 2 by 6. Or in other words, A equal to finally minus 1 or 1/3. Okay. So this is the final answer I am getting A. Now, but A is a fraction of V1 and V2. So therefore, this answer cannot be agreed. So finally, I get for maximum power, I'll write it here. For maximum power from wind. So what is the condition? So I'll get A is 1 by 3, which is nothing but V2 by V1. So therefore, V2 should be 1/3 of V1. So only that condition. So in other words, let's say this is the turbine. So from here, let's say 9 meters per second is the wind velocity, V1. Then V2 should be such that it should be 3 meters per second. Only then maximum wind power can be generated. So that is the condition. So P max will be there, mechanical power will be maximum. This condition, 9 meters. If it is here, say 15 meters per second is the wind velocity. Here V2 should be made 5 meters per second. But this one is not under your control. This value is from the nature, whereas this one is under your control. So how do you control this? By controlling the pitch angle. So let's say pitch angle is made like 30 degrees, and then you find what is the V2 and so on. You can accordingly you have to do that. This also tells an interesting thing. If I install one more wind turbine behind this, so here 9 meters per second, and here it only gets 3 meters per second. So the second one will not be able to generate a lot of power. And finally, the output power will be even here it will be 1 meters per second, but then here itself is not. So when you keep the wind turbines, it cannot be one behind the other, in a very close distance. So usually the wind turbines are kept in one row facing the wind, and after long distance again there will be one more row facing the wind. So if the wind is like this, so the wind turbines will be like this. Again, after long distance, one more set of wind turbines. So like that, it will be there. So anyway, so we got this condition. So just bear with me for 2 more minutes. We'll finally find out what is PM. So in order to finally find out what is PM, so again, I'm using this relation, what I got here. So PM equal to 1/4 rho A V1Q 1 minus 1/3 square plus 1/3 minus 1/3 Q. So let's solve this part. Okay. So see 1. And V1 cube, I will leave it as it is. And then this one, what I will do, so this one can be, say 3 cube is 27, right? So 1 by 3, I'll multiply 9. So this is 9 by 27. And this is 1 by 9. So I'll multiply by 3. So it will become 1 by 27. And this is 27 by 27. So I just made the common 27 so that I can find out this. So 27 minus 3 is 24, right? 24 minus 1 is 23. 23 plus 9 is 32. Okay, so 1.225 by 4 A V1 cube. So this will be 32 by 27. No, I think somewhere I'm making a mistake. Or maybe it is fine. So now let me find out the, I think you can find out the final constant from this. I'll not go further here because it's trivial. Okay. So, so this sets a limit of how much maximum power you can extract from the wind. Okay. So again here, I'll try to take a pause and maybe I'll wait for some questions if you have.
So this is development and PLC.
And we'll take signature on this, which is okay. Vision and what else we need?
Sir, please unmute, sir.
If this is okay, then you can do
Sir, please unmute your system, sir.
it is not code is there.
Sir, please unmute your system, sir.
It is
So yeah, I'm here. I was just waiting if somebody has any questions or doubts.
these things is available, sir. You can learn it.
Yeah. So any questions or doubts, please feel free to ask right now, because from that I'll get a sense, what your doubts are, what your expectations are.
Participants, please, if anybody having doubts, please raise your doubts.
So if that is the case, I'll just take a break for 2-3 minutes. I want to show, since we have time until 12, I want to show one demo which I've developed, so that it may not be exactly related to the wind, but I think it will be interesting for the participants. So can I join back by 11:20?
Okay.
Yeah, I'll be still there. I'll not mute. From 11:20, I'll continue one more session.
Okay, thanks.
Yeah. Hello everyone. Sorry for the delay. So I thought I will, since we have some more time left, I thought I will show you one interesting demonstration. Yeah. So you are able to listen to me? Hello, you are able to listen to me?
Yes, sir.
Yeah. What I thought, since the more time is there and whatever I wanted to cover on wind, I have basically covered it. So I thought I will go back and show some demo for the participants. We have developed a small power monitoring circuit, and I would like to show that first. So you are able to see my screen, right? I'll just switch on. Yeah.
Yes,
Now,
okay, sir. Now, okay, sir.
Now you are able to see one simple electrical board with one plug and one switch. So I can connect a load, so something like this, and if I switch it on, you can see that the light is switched on. Okay. Now what is interesting is that now I'll share my screen. And I'll go to one Google spreadsheet. Okay, so I think this is the spreadsheet. So here you can start observing. I'll increase the magnification. So here you can start observing that some data is coming into the online Google spreadsheet. Okay. So the power rating is coming as 8.8 watts. Okay. The voltage is 235, current is 0.06 amperes. And energy, this is just a cumulative energy. So right now it is still 0. And the frequency and power factor. So like this, I'm getting some readings. So if I even scroll down, I can get. So as time passes by, every 5 seconds, I'm getting this reading. Now what I'll do, I'll switch off the power, okay, and then see what will happen. So I'll switch off the power. So I think you heard the sound of switching off the power. So now you can see 0.4 watts. Okay, so the reading of the power is reduced, and you're getting a small value. In fact, we can visualize this also. So I can just insert a chart. So right now on your screen, you are able to see this chart. Okay, so this chart is again updated. So if I switch on the light now, so I just switched on the light, and we'll wait. So now immediately you see the power increased to again 8.8 watts. So, and it will continue to remain at 8.8 watts as time passes by until I again switch it off. So basically what I am demonstrating right now is kind of a real-time power monitoring kind of system. So where you can monitor the power in real time. Okay, so how it is done, I will just quickly show. In fact, I have made a separate video on this which you can refer, which I'll tell in the end. But it is so far like this. So I will again switch back to. So I just switched the power off. So again, the data, it will go to 0.4 watts. So now you can see the power has come down to 0.4 watts on your screen. So now if I stop sharing my screen, so again, you can see on my camera. So the setup is like this. So I can switch on the light, and the power will show it will be showing will be increased and like that. So what is in the back of this? So I would like to now show that. So in the back of this, we have some IoT module. Okay? So you can see. So this one is called ESP. Double. This one is the power measurement module, and this one we are not using right now. This is for storage. Right now we are not using, so you need not worry about it. So these are the two important things. I'll just once again show you, and you can see this is a kind of a current measurement coil. So this is a CT. It comes along with this particular device. It's about 1,000 rupees, and this one is about 300 rupees. So within 1,500 rupees, you can build this kind of power monitoring. We can monitor any appliance. So far, any questions you have, any doubts you have as of now? Are you following what I'm suggesting?
Participants, if any doubts, please clarify your doubts.
Okay, so I'll just continue. What I now do is just show the connections, because in this the wires it is difficult to follow, but I will show it in an easy way. So the connections are like this. Let's say there is a main supply. Phase. Okay, so this is, you're able to see, right? This is phase and this is neutral. Now here there is a switch. I was operating one switch, right, with my hand. So there is a switch, and after the switch there is a basically there's a plug point, and this plug point is connected to a light. So this is the switch S, and this is the plug point. Okay, and this is the phase and neutral. Now I want to monitor how much is the power being consumed here. So for that, there is a device called PZEM. So I'll do it with a different color. PZEM. So if you search by this name, you will find it is available online. PZEM 400T. And it's a 100 ampere module. So this is the power side, and the so there is a phase. Sorry, I'll show with this color. So first is neutral, next is phase, next is S2 and S1. So neutral connects to neutral, phase connects to phase, and S2 and S1 connect to a current coil. Okay, so the current coil is like this. You connect to S2 and S1. So this is the power side connections. So one will measure the voltage, one will measure the current, and from that we'll be able to know the power and power factor, everything. So meanwhile, on the other side, I have that ESP module. So I'll write that module. So ESP 8622. Okay. So it has terminals ground and D7, D6. So we are using this digital input terminals, and then the voltage terminal. Okay. So similarly on the here also, there is a 5 volts terminal, there is a RX that is receive, and TX that is transmit, and then ground. Okay. So and then again obviously the connections are ground goes to ground, transmit goes to D7, receive goes to D6, 5 volt goes to voltage. So once this is done, this has Wi-Fi capability. Okay. So through my Wi-Fi, it can send data to Google spreadsheet. This is the simple connection. So whole of this we kept in that one box, and then we are able to do the power measurement. Of course, we have to write some software code in this. Okay, so this has a some software code. So this is the simple connectivity diagram of this, and the code also I can just briefly show you. I have to share my screen, just a minute. So here on your screen, what you're seeing, this is like the simple code. In fact, I have provided this code also in one of the videos in my YouTube channel where you can use this. And so here you can see the voltage connections and voltage readings are happening here. And then basically based on that, message is created and the message is sent to Google spreadsheet. And the output of this will come in the form of data that I was just showing you some time back. Here you can see the data. So now here you can all see it is continuously in off position. So again, just for fun, I will switch it on. So what I have to do, I have to put this light here. So I just switched it on, and again we will notice that the power measurement will again now go up. So you can see on this, it's a simple monitoring system. So what I have done on this is I just show my so if you go to playlist, so one of the playlists is smart grid design and implementation. So in that playlist, I have explained how this thing works. So each and everything step by step I have explained in this particular video how to make the connections. So you can see. So all the connectivity connections are made in this, and then the software, what needs to be written, the software also I have explained it here. So if you follow these steps, you will be able to make the power measurements. So again, any doubts on this? Have you seen any like this low cost power measurement device using IoT?
Participants, if anybody having doubts on IoT, please clarify your doubts with sir.
I think I would like to end the session here because I have whatever wind energy topic I had covered, whatever I could, and as an extra, I have also shown this module. So on this, if anybody wants to have further discussion also, please email me on my email ID. So I just, is it okay if I can end the session now?
Okay, sir.
Yeah. Thank you. Thank you so much.
Thank you, sir. Thank you very much. Thank you, sir. Thank you very much for your valuable information.
So for the detailed thing, please refer to the playlist which I just showed. If you go to YouTube and then search with my name, you will find my channel, and all the videos are organized in the form of playlist. So please visit that. You will find a lot of more information. So thank you.
Okay, sir. Thank you, sir. Thank you very much, sir. It's escaping. But how it is correct? That's what the time. Is it wrong? I thought you with the name. Calling you evening, sir. Is it actually? I've seen. I did not get. No. Correct, sir. I was still only take that one. So, sir, number of participants. Number of participants are equally. Now, sir. 12:30.